got a very full room again.
What are you telling? Full room again? I don't know. Mistake or the couldn't detect the signal.
Last week. There's like stuff like tape.
Well, thanks for considering this as an option for in your plans to come and do something here. So, who we are and what are we doing? There is a list of projects that I'm still developing. It's a little bit, but there are several people who decided that the projects on modeling of the electron propagation in true Cartesian space makes some sense and interest. Where are they? So, Mark, Megan, Luke, Jan, Braden, London. That's it. So I'm not surprised if the rest of people do not show up. If you are not planning on the top and you are coming, it's a big benefit for you. So, what does it mean, propagating in real space? Of course, everywhere there are... No? No? Yes. Focus. Focus, please. So everywhere there are difficulties, but sometimes there are some simple things, and this is the simple thing in top of the table range of projects, so that we do not need to care about changing the mass. In all other projects, we will propagate not electron but normal mode of vibrations or reaction coordinate or protons which have mass at least 2,000 times bigger. And it will change the time scale. Right now the code is tuned for typical time of electron motion and for typical electron mass. For other projects we will increase mass and increase time. And if you do it without right preparation, it will yield a lot of errors. But this is a little benefit. Autofocus is not very focused. So up to now we were propagating particles in one dimensions in some fake potentials that were made up by us. And they were either too simple or primitive and were not related to true molecules or materials. We even didn't pronounce the word atom in the course up to now. It's time to tell this word right now. So, since you are in chemistry or nearby subjects, it's not a big wonder for you that materials, molecules are composed of atoms. And today we are going to recognize it in our encoding. So in addition to electrons, there are atoms, ions, and they are very attractive for electrons. So due to electron to ion attraction, the potential should be negative, right? To attract electrons. And if you have a single positive ion at position x0, so if you have here our position, here our potential, here is 0. So for free electron, potential is 0. If you have a universe that consists of a single atom in one dimension, we are not ready for multi-dimensional things here, then it should be some shape that will be centered around this atom, right? So if we are far from doing quantitative science, if you want to do the first step, we just need a dip near the place where we put the atom. So we need to specify its position, we need to specify how deep it is, and it is related to what? Ionization energy, right? How much it takes to promote an electron from the bottom of the potential to make it free electron to escape. So electron ionization, and we need the width of this shape, which will be like ionic radius that you can pick in tables, periodic tables from internet, or just guess if there is a crystal lattice with tightly packed atoms, the width cannot be bigger than interatomic distance. It should be some number like half of the interatomic distance for approximate for the first approximation, if you have no data and no guess. Okay? Which function would you recommend to use to mimic that potential? Yes, we do not know, we do not play with too many functions. Again, the project is your free creative activity. You can do anything you like. I'm just giving little hints what is possible. So we take Gaussian with negative sign, and then we fit its parameters that it will match position, width, and electron ionization, which could be atomic position minus E minus x naught squared, some width parameter, and here we need normalization and we need this electron ionization. Right now I'm not taking care of the exact constants, but if we set up our variable for potential in this form as function of x, which is defined, we have the grid points for each place in space, then it will be a model for a universe composed of single atom, right? I never did it myself, but I had another undergraduate student who was doing it for me in the past. So he carefully looked for numbers and interatomic distances and parameters. So it looks a little bit better if instead of exponential there it is a little bit modified. So it is modified in this way that it will, you see, if this is 0 and this is 0, it will be inverse exponential as we discussed. The parameters that I'm going to offer in the code, well, I have already offered, you see it in your code, are tuned to silicon atom. One can look for in tables for the parameters for other atoms. It's not very complicated, and choice of silicon is because it was primary material for photovoltaics, and it is being slowly replaced by other materials, but still it takes it niche. If you hire a company that will install silicon panels on your rooftop, PV panels on your rooftop, there is a 99% that it will be silicon based. So, and if we have more than one atom, we will need to escalate and repeat the same potential at the offset of the lattice constant of the crystal. And then again and again. But let's start from the one atom and see what happens. Again, I am a little declaration. I'm not going to do any of the research projects that you have chosen. I'm just covering the basics and showing the way how you can modify and model problem of your interest. Okay, so going to the code. So the changes in the code are applied to the same version as we did in the last lab number 9, and new lines are inserted from 44 to 60. So the parameters are set up in the atomic units, and the ionization potential minus 0.42 will correspond to approximately minus 10 electron volts. And atomic units of width of length. One atomic unit of length is 1 Bohr radius, which is half of angstrom approximately. So 2 atomic units of length is about 1 angstrom, which is corresponding to order of magnitude of ionic radius. And later you see that there is a parameter for interatomic distance, about 6 atomic units, which will correspond to about 2.7 angstrom, which is atom to atom distance in crystal lattice of silicon. So if we look here, there is a strange, well, crazy thing, cycle from 0.5 to 0.5, which means there is no cycle formally, it's only one number. And here we do have this equation, which is expected to model the potential well for one atom. So I am going to just run the code. So we set up zero momentum, and the initial position of the wave packet is approximately set up near the center of this atomic position. So you see, if you intentionally set an electron inside this if you intentionally set electron inside the well, you will not see much change of the shape of the wave packet, which is kind of reasonable. It sits there and it demonstrates something like S orbital because there are no humps of the camel. So the time is still going on, but you do not see much of the motion by human eye, and you do not see much difference between different methods of the code. And the offset, which symbolizes the total energy, shows that it is below zero. So it is energetically favorable, stable situation when electron is inside the atom. It has been attracted. So please practice it just for your pleasure. I think it should work on any machine. I see that some of you have already found a way to modify the code further. This machine is a little slower than yours because of the video. So I should think twice before running anything. So what would be the natural thing to check here? Guess what we are going to do? I know that 1 out of 4 has already committed it. So look on each other and ask each other. Around the audience.
I'm looking at you too. We're going to make the particle move, or the electron.
Yes, but is it, I know that we were suffering a universe without atoms for a long time, and we are so happy to have at least one atom, and now we can apply all our strong knowledge about machinery, how to describe it. But is it enough for us to have only one electron in the universe, or one atom in the universe?
No.
So, in this context, what would be the natural experiment to check?
2 atoms.
Yes, and then we can try 3 atoms to be liberal. And
That's what you mean by 1 over 4. Okay.
so we can, in fact, we can fill all space that is provided to us in the code, all Cartesian space, by many atoms and model the bulk. So right now we are going from 0.5 to 0.5, but we can put like number 4 here. And so what is going to happen? There will be 4 atoms in a linear chain, right? But there is a bare, plain, literal codes, and there is our human interpretation. So why don't we think that right now we had infinite number of atoms in the linear chain, but we were looking on on them only across one direction. And now we will have a slab with thin film where along X and Y, well, right now we call it X, along Y and Z direction, there are infinite number of atoms, and in the X direction, we have either monatomic layer or diatomic layer or 3-atomic layer, or let's probably model 4-atomic layer. So since photovoltaic technology is thin, well, you would not argue if you have seen solar panels that they're flat. Therefore, they're made of thin films. So, save.
So
Yes?
what's the 0.5 for? So 0.5 to 0.5 gives you one well, but if you increase it to 4.5 to 4.5, that makes it 4 wells. Why 0.5?
I was super cautious. If you place singularity in 0, just I have a superstition that something wrong may happen. It's better to avoid zeros.
Okay.
So right now the atoms are centered either at 0.5, or you can start running index from negative and
Okay.
avoid zeros. But there is no true science behind this.
Oh, okay.
Another thing, if we set up one well in 0, and then we will run equal amount from the left and right, it will be always odd number of monatomic layers. And by some aesthetical reason, I like even number of monatomic layers. So if you select this project, and no one forbids you to play and center it anywhere you like. Okay. So right now we do center the electron near the position of one monatomic layer. But you see, if you look here, the space between atoms is a little bit lower than zero level, because they are forming chemical bond. They are not independent, and there is a chance for electron to tunnel from atom to atom. And in fact, if we are describing solids, then like metals or semiconductors in excited state, the electrons are it's in the chemical language hybridized orbitals. So the electron is delocalized over multiple atoms. So and on chemical language it is hybridized molecular orbitals. And here we started at the leftmost, and then as time passes by, we see that electron distribution prefers to stay at the atomic centers. But it is allowed to distribute across several atoms, and we can look that the center of this wave packet moves from left to the right. Probably if you wait long enough, it may reflect back, like an electron inside the thin film. Before, we were talking about the thin films as a particle in the box, without structure. And now we see that it is not a silly box with nothing. It is a box formed of atomic structures. By the way, I set it up to 5, not 4. Okay, 5 monatomic layers. And also, at the very beginning, the average width was coming over only a region of space corresponding to one atomic layer. Now you see it kind of takes all available atoms. So if we remember particle in the box, in the ground state, it is expected to have a shape protruding from left to the right edge and be in approximately sign, slowly changing envelope function. So let me run across the class and see if everyone enjoys this setup. If everything works, yes?
What did you do to get multiple wells? Mine, no. So I changed 4.
No.
Oh.
Replace 4 to 1, and then put, instead of 0.5, put 3.5 plus 4.5. Yes, minus 3 from negative to positive. Yeah, that's enough. Run and see what happens.
Sweet, thanks.
So what you started to do, it was injecting an electron with very fine resolution. I don't know which apparatus that maybe electronic microscope.
Oh, yeah.
So you inject it on a very tiny spot on the atomic resolution, and then you see how it scatters from
Yeah.
atoms. Probably can be this.
I'm having as much fun today, Landon.
Huh?
Still playing with it.
What else? How can I enjoy this code and play it further? So maybe ready? If you just go one line up.
Can you shoot an electron at him?
Huh?
Can you shoot an electron from the left?
Yes, yes. So you can see the capture
Top variable.
of an electron by.
Yeah, so start X.
So I mean, I did it already, but
Oh.
And in the one of the previous labs, there was a line, I do not know how it appeared, that 1 electron volt is equal to 1 kilocal per mole. This is wrong. I wiped it off.
It might just have too much energy. It wouldn't care. If you do know that, right? No? Okay, that's it.
So I'm behind Christian, who did this experiment a little ahead of time. So this can be interpreted as the electron microscope with fine resolution, with subatomic or atomic resolution, injects an electron ray at specific place, and then it scatters through this several atomic layers and distributes over everywhere it can. Also, we can think of diffusion of electron across, but it's not a diffusion equation. It's not a finite difference Boltzmann. It's more quantum Schrödinger equation. So it is dynamic. If you inverse time, it will come to initial state. While in the dissipative process, it will never return back. And see, it wants to take the whole available space. So I'm going to play a couple of other little experiments. One of them will be changing the width of the initial wave packet and see what happens if we intentionally create a delocalized electron that approximately covers all electrons. And see, whatever we do, there is a minimal electron density in between atoms, and it always has a maximum on the ions, right? So in some sense, when we want to connect this figure, this image with particle in the box, there is a so-called Bloch theorem that you will be exposed to if you take solid state physics. If you will not take it, you probably will not see it. The wave function of electron in solid can be decomposed on a product of atomic wave functions that are localized on each atom, here, there, and slowly changing envelope function. So if we look on it from the bird's eye, from strategically, the atomic functions are boring and they're always the same, but the envelope function is dictated by the shape of the nanostructure. So if you look on these things with rough resolution, we can build a continuous function that probably picks maxima at the position of ion. And then this one will look something like second harmonic, like 2 humps. So it is a connection between particle in the box and atomistic modeling of nanostructures. So I'm trying to increase the width of the wave packet and see what would happen. So since the initial wave function is not an eigenstate of this problem, we will always see some motion. But if we guess an initial function which is relatively close to eigenstate, for example, ground state, then you'll see that there is a little motion, but again, strategically, from roughly looking, it will keep the shape with one maximum. So it is relatively close to the ground state of thin film of a given thickness. From 60 to 140, it is about 80 atomic units. Should be twice as less angstrom. So about 40 angstrom thick nanostructure. You can always also build, I'm not going to do it, but if you are interested in modeling solids nanostructures, you can fill the whole space by atoms and model periodic solid and look how the electrons are going through it. And also initial state can be selected as a plane wave rather than shaped Gaussian. So return to control page, okay. So if we will look back onto topics for independent research projects and choices, you will see that many of the problems are formulated as electron transfer on interface of two molecules or two solids or solid and molecule. So in many engineering aspects, in many chemical aspects, in many physical aspects, the broad range of problems can be reduced to charge transfer between donor and acceptor. If right now I'm going to talk a little bit about silicon photovoltaics, it's just a little quicker with this setup, but then we will expand further. So if we are looking on solar panels, they are built of two layers of silicon. One is p-doped, another is n-doped, right? Which means that silicon atoms with very low concentration are replaced either by phosphorus or aluminum or other atoms that are neighboring silicon in the periodic table, like boron and arsenicum. And then it makes one layer to hold too many electrons, a little too many, and another too few. And then upon excitation, photoexcitation, electron can migrate between these two layers. So this is what is going on in silicon technology, and we can model it here by picking one of the atoms and making it lower, which means it will be lack of electron, it will be electronically accepting doping, or we can lift the height of one of the atoms and it will be electronically donating layer. Or if we do not want to bother ourselves with silicon and speak about charge transfer at the interface for very general photovoltaic technology, then we may speak of semiconductors that have different ionization energy. So you can take half of the layers a little bit less ionization energy, another half a little higher. And then our goal would be to observe how the electronic density prefers to concentrate on one side over another. So this is something practical that we can explore and see on the yield of this reaction of electron transfer. So right now I'm not feeding exact values of the ionization energy. I'm just roughly setting it one system as a donor, another as acceptor.
You're going to want to rename one of those.
Huh?
You have two of them that are both called Barrier 4.
Yes.
It doesn't care.
Barrier 4 is where we accumulate. So each time we pass through the cycle, we add something to this accumulating variable.
Mhm.
Here we run cycle from -6 to 0, whatever, -6, 5 to 5. And we have the acceptor that, we will have the donor. Then we continue it from in other range, and then it will be acceptor, deeper. Make sense? It's one potential for two layers of different materials. But since we have only one electron, only one simulation cell, the variable V that later is set up like V equals to barrier will include everything, all types of atoms that we have in simulation cell. So at the initial time, it was approximately equal, but now we do anticipate that there should be charge separation. There should be flow of charge towards from the donor to acceptor. And at this step, when the dynamics will be over, our previously composed observable for reaction yield, this integration of left and right side of the cell will be extremely helpful. It will answer us how quickly this separation of charges happen.
Is that realistic yet, though? Because if you initialize the particle purely on the left side, it won't go to the other side because it can't feel those potentials. Or is that wrong way of thinking?
So if you initially prepare it on the left from the interface, and nothing on the right, then if there is no big barrier between on the interface, if two layers are in direct contact, then there is a chance of tunneling.
But very small.
Well, if you go from right to the left, to energetically unfavorable, it will be, you need to activate it by either photoexcitation or the thermal activation. But downhill, it always happens.
It's nap time.
Hmm?
It's nap time.
Nap time, yeah. I know what we will do in the couple of other little experiments. Let me record it before I forget. So we will apply voltage, and we will insert vacuum. So model a situation when they are not in direct constant, but a little bit aside from each other. So through space charge transfer. Okay, so here at the initial time, the charge is equally distributed over both sides, and at a relatively quick time, 50 atomic units, which is of the order of a couple of femtoseconds, it disbalance to one side of the cell. So the rate, how quickly it goes, and then it stays in more or less steady state. Rate, how quickly it goes, does depend on the contact, on the, if the, right now it is very efficient through bond transfer, because atoms on the left and right side are chemically bonded. It's not always possible. Sometimes this interfaces, like there are nanostructures that brought into contact, but they are not in the, they can be physisorbed when there is a little distance between them. And then this rate will change.
So speaking of, so this is modeling of solar panels, you said? This is like solar panels, role modeling of some sort?
Yes.
So when you excite when this goes, or the electron up into the next one, how does it like continue to cycle? Because if you excite them all to the next side, then the other side would be deficit of electrons and the cycle would end.
Your question is legitimate. The answer does exist.
To advance.
And we can model it with the tools that we have in class. It will be just too much at once. So right now, we are modeling the open circuit regime, which is characterized by open circuit voltage, the potential between two layers. But in practice, this layers of donor and acceptor are both interfacing the metal conductor, and it is connected across the cell with a load. Okay. So if it is favorable for separated charge to generate current goes across to the left and right, and you can use this current to drive something useful.
Okay.
Since we do have periodic boundary conditions, we can insert metal layer, maybe with some resistivity across, and then it will be complete cell. But the most important event is charge transfer on the PN interface. Therefore, we are looking on it in the short time regime. So we are not coming to a steady state when it recovers. If you are following the literature on the dye-sensitized solar cells, on the Grätzel cells, the charge transfer between dye, like ruthenium complex and titanium dioxide as semiconductor, also generate this single event of redox reaction, but then it needs to be regenerated for the next cycle. And it is performed through iodine-3 shuttle in the solvent that circulates between this donor and acceptor and does the counter current. But it is needed, it is correct, but it is secondary. It is almost trivial steps. But the charge transfer is the bottleneck that needs to be optimized. Therefore, we are simplifying, looking only on the heart of dragon rather than the rest of things. And what else? And we can also place charge on one side. So what we are modeling right now, we create the initial density only on one side. So this absence of a couple of atoms models the physisorption rather than chemisorption. So there is a little insulating tunneling regime. And now the transfer does depend on the excitation of the initial electron, not only spatial localization, but overall energy, the distance between these layers, temperature, and as we will model in a couple of, well, not in a couple, but in like 20 minutes, the presence of voltage. That was choice number 1 by Mark. So you do see that upon forming of this vacuum or insulating layer, the transfer goes much slower. So it, although it is energetically favorable to go to another slab, it goes orders of magnitude slower than it was before. So we are like half of the reaction time over, but the electron still stays in the original slab. And in addition to our primary experiment, we do have primary event of transfer between these two dips. We have an artifact of our periodic boundary conditions. So there is something, some density forming in the vacuum region on, aside from the systems. If you plan, it's a question to Braden, who likes to program. If you plan to modify code, especially for visualization during the presentation, you may set up a running time like t equals, and then think that will run and show how far one is in the progress. So you see that there is the transfer is going on, but it is much slower. So this distance of 2 atomic layers missing between slab, it is almost insulating. It forbids the transfer. So probably it is not the best structure for photovoltaic generation. So one may need to establish some bridging structure, bringing them closer. So let's try to apply voltage, which will be a general approach both for photovoltaics, because one can apply it, one can run this photovoltaic cell not only in the open circuit or short circuit, but in between, where the different voltage applied to this photodiode. At the same time, if these slabs are, right now I will not have time to exactly model metal electrode and analyte molecule in electrochemistry, but the simulation cell will be very, very similar if you want to model the electrochemical setup for measuring reduction and oxidation potentials. So one potential for electrode, another for anode, and then we are going to model the voltage. We'll be just adding overall slope to the molecule, that to the simulation cell, that will favor or disfavor charge transfer between components. So we set up the voltage as strength of electric field times position. So the potential will be linearly changing for constant strength of electric field. And we can change the value and sign of the field, which will mean the swapping the contacts, plus and minus. So although it's not favorable to overcome this barrier, but in presence of helping electric field that will accelerate electron, you see that some portion of the wave packet is getting already transferred, and within the slab here, it leans towards this side, because there is a analog of force. There is a reason for it to go there. Still, this distance of from 90 to 10, the distance of several angstrom is very large, and it is hard for electron to overcome it. So we are not going to see terrifically high efficiency of the charge transfer. In reality, donor acceptor are typical. Well, for situations when charge transfer is happening, donor and acceptor are typically approaching to distance of few angstrom, not 10 angstrom. But if you're planning to perform your independent research in this direction, you may model different materials or different molecules by tuning the parameters, the ionization energy, the atomic radius, or you can model a molecule or material just by a slab as a particle in the box. It is not a super big approximation. With all other approximations, it can be still valuable. So, distance between donor and acceptor, ionization, depth, and other parameters. Let me walk through and see which if everyone is happy, we need something.
It has been much. Well, it's not on my section anyhow.
Yeah, but well, something will be.
I'm still trying to figure out this part right here. Because wouldn't this, I mean, if you were to, cause I don't know, as far as what I saw, you just copy and pasted this. So wouldn't you end up with the same potential on both?
No. Let me
I don't know,
let me convince you.
Yeah. So I had to restart from scratch. Well, not from scratch, but.
I think let me offer you something to think about, and then we can argue or agree.
Yeah, copy paste. That's how we got two different potentials. So like at the end of this, buried force is buried full. And that's what you're setting voltage to.
So you're adding, so barrier 4 is a list or an array.
Right, yeah.
So the way it interprets barrier 4 plus some other shit,
Yeah.
which is also an array, it adds
One?
to the end.
What do you think about such function? So it is summation of Gaussian function, and let's put to make it completely related to what we do minus. So summation of Gaussian functions, which are offset from the center by 0, 1, and 2.
Mm-hmm.
So we're adding them together.
Yeah.
What should I? How should I draw this function?
You would have like little Gaussians at different spots.
And for negative, it will be like 1, 2, 3, right?
Right.
And instead of writing equation this way, I can put the variable like k, and right here summation for k going from 0 to 2.
Right. Well, okay, so like I didn't see everything that you did. Like when you copy and pasted that section of code, I didn't see if you like changed anything.
Okay.
So what I'm not understanding is how you got different potentials. Like you got one potential well here, and then you got a lower potential well here without.
Okay.
Because
Yes.
from what I saw, you didn't change anything. Like with the.
I did. Let me show it.
By the
No,
time I got
it's better
more
to.
code again. I mean, it's already gone. So.
Let me just write equation once again, and then so two summations. One from, let's say, from k equals from -3 to -1.
Right. Right. Yeah. So you got two different things. Yeah, that's fine. Yeah.
So we won't use each of the extra codes done by Photovoltaics
Okay.
and modify the positions of each one.
Okay.
So like one at negative 10.59.
Okay. That makes more sense now. I saw the code from Brayden's laptop. It
Okay.
makes sense to me now. Yeah.
Okay. So let's check what did you get. I wasn't saving the screen image, although I probably should. But by naked eye, we do see that applying each makes it percentage of transfer larger, the yield of transfer is bigger, it comes to 0.1, and it goes maybe a little quicker. So there are several parameters that increase the rate and yield of transfer, and in all projects, no matter what you select, we are going to explore how this curve will respond to any change of the circumstances, like voltage, distance between donor acceptor, or temperature. As an analog of temperature, we can just change the momentum, because momentum is a measure of kinetic energy, and there is no ensemble average. If you want to be absolutely correct, you need to have the same momentum but oriented in different directions and then average over it. But right now let's, I wouldn't say cheat, but make our life simpler and orient momentum towards the product, towards the direction of transfer. Oh, okay. This momentum is too high. So momentum 2 in atomic units, it will correspond to ramping energy by. So 1 atomic unit is 27 electron volt. This is about 30 electron volt, and then it will pass through independent of any potential. So probably I was too optimistic about the numerical value. So right now it's something that will push it across this barrier and even through the sides of the periodic boundary conditions. So maybe for more realistic things, it should be f fraction of 1. I'm even not going to record it.
I think if you choose 0.6, it's just below.
Okay, let's try. Thanks for the prompt. It looks like it is helpful. It overcomes the barrier with a majority of density. Maybe it's too much because then it goes to the vacuum, but it is due to ramping by the voltage. But right now, in this little example, we are mixing everything together. It's like temperature, voltage, and it would be more reasonable to inspect influence of these two things separately first and then merge them together. It is reflected off because here the value of potential is -1 and next it is +1.
Ah,
So it looks like very high barrier.
okay.
And on the time corresponding to more than one single pass through the periodic cell, it's not very reasonable to use this code. Well, not the code, but we need to set up the range of parameters that would correspond only to a single pass.
Yeah.
So we are looking too far in time. Or we can expand the size of the cell, but it is already large enough. Like 200 atomic units is like 100 angstrom, 10 nanometers, which is huge for any atomistic model. Like if you do computational chemistry, all your models are restricted within maybe 2 nanometers maximum, plus maybe a little layer of solvent or vacuum. Like 3 nanometers is considered as a huge one.
Okay.
So the benzene molecule will be like this much on the scale, of the size comparable to 1 dip. Okay. So we have at least 50% transfer, even sometimes even more. Thank you, Brian, for suggesting reasonable parameter. What else should we cover today? Give me a little assignment or discussion point.
Dependent potentials?
Okay. I will record it in case there will be more than one subject. TD potentials. Any other subject discussion points that you may find relevant for your work? Is it enough input for your project? So you may play with parameters of the potential. Organization of the network.
Project in 3 different classes, so
Sensitized.
big fucking project.
So if I can, I'd like to maybe shoot a little solar cell. Then I can characterize some solar cells for my optics project, right? And I can like simulate a bunch of then I put all my results into a database and use that as my database system project.
Thanks.
It's still, no, it locked me off actually. Intriguing.
Any comments, questions, or requests? No, not yet.
Not that I can think of. What?
Questions from your side to my side.
Oh, not that I can think of right now.
I do have a question from you to me.
Okay.
Did you got a special email that was
Yes.
sent to you only and not to the whole?
I did, yeah.
Yes.
I
Did
got
you
that, yes.
did you got any idea, or is still a mystery for you?
I haven't had a chance to read it or anything. I mean, I just looked at it
So-
when I got here.
I'm going to tell a little bit more things for everyone, but now a short message personally to London. So he was among not very many persons in the class who selected a subject that is close to my heart. Although he selected as number 3, but I will make it his selection number 1.
What was your first selection?
Oh, I just went to like reactant to product as my first one. This is like a kind of a, I don't know. I mean, it's a basic thing. That would probably be the. But if I do a solar cell, then that might work out nicely with my optics project that I also have to do.
Touche.
Okay, so you see in each chapter there are 2 sections, model approach and ab initio approach. So model approach means that we do what we did up to now. We just curve potentials based on our scientific intuition and imagination. And there is a little bit more solid approach where potentials are not designed by humans, but extracted from atomistic modeling, from the computational chemistry course that you guys haven't taken yet, but there are a couple of postdocs and graduate students who can help you to derive it. Or if they're not energetic enough, I can play their role. So you know that the things that we were doing right now, putting ions in the right place and then letting electronic clouds to form around them, is a part of a very special and nice branch of science known as computational chemistry, where you just draw any molecule by putting atoms in the right place and then letting electrons to fit the place at the right energy levels and right positions. So there is when it happens, the last electron that is added to the system feels attraction not only by ions, but also by the rest of electrons that are distributed. So there is much less attraction. And this potential that the last electron is feeling can be recorded in the atomistic modeling and integrated over 2 dimensions and keep only 1 dimension, and then sent as an email to a hero who selected as a possible option. So if London will explore his email, there could be a couple of files that will include a table. The data that would correspond to the V potential, but each point there is not set up by analytical formula, but provided from atomistic calculation by special procedure. So this data, this set of data points, which is like 300 numbers,
Yeah, it's pretty big.
need to be loaded into the MATLAB code at the very top, at the place where you tell V equals something. Instead, you need to write V equals load, and then log put point Z, or whatever name of the file is. It may not work right away. There is a little tweaking to make correspondence about step size, which is like 0.4 in our modeling, 0.4 atomic units, and there it could be a little different. But number of grid points, right now we set it to 500, here it can be a little less. But it is very trustable formal procedure to get potential. So, and if you run electron dynamics with such potential, it converts the project from the range of educational projects to intermediate state when it can be a seed for something publishable. Okay? You have an idea what to do. Try to read it, place it in place of V, and run and see what happens. It's not easy. You will face a couple of failures, but they are minor. They can be resolved within like 15 minutes.
So do I load in the space or the bond file?
I'm continuing a little message personally to London. What you have selected, or what I have selected for you. So his choice was dye-sensitized solar cell. Silicon technology may die, and it will be possibly, I don't know the future, maybe replaced by perovskite technology. So let's highlight perovskites, which are in the news for the last couple of years. And the perovskite interfacing titanium dioxide for electron acceptor, same as regular DSSC. But there is a debate in the community what would accept whole from perovskite. And there is a specific organic dye that, since I do not have chemical background, those of you who do may suggest, like, how to call it?
Trisphenyl something.
Mm-hmm. tribenzenamine? Maybe. So if this molecule is interfacing the perovskite semiconductor, then it will accept positive charges, holes. And the rate of the hole transfer, which is as important as electron transfer, does depend on whether it is physisorbed, so through vacuum connection, or there is a little CH3OH group, that this group similar to methyl.
So hydrogen bond.
Yes, and then through the bond, the transfer is expected to be 1,000 times more efficient. So if you do not refuse this subject, your main outcome that you can prove right or wrong is that if you repeat simulation twice, once with the space and once with a bond, you'll see 1,000 times difference in the rate of transfer. With space, it will be 1,000 times slower. With bond, it will be 1,000 times quicker.
And because the bond, you have like some electron cloud connection or something?
Mm-hmm. Hybridization, yes.
Okay.
Hybridization between donor and acceptor through linker group.
Okay.
Clear? So,
Yeah. I'm not used to reading like chemical diagrams, I guess, so I'm just like trying to visualize that.
send request to me and to another person who is on the email. There is an address to you and to
Right, and Aaron, yeah.
yeah. You will get more information that you can process. Okay, what were other? I hope it was entertaining not only for London. Time-dependent potential. Although I'm imagining you doing silicon PN junction.
I don't know, I kind of don't want to do that anymore.
Oh, okay.
So we just did that. That's fun.
Oh no, we didn't. You cannot convert what I'm showing here immediately into report of the projects. They are independent. You do something new, and we didn't model exact literal potentials of P and N doped, and you may elect to select atomistic data for these potentials as well. Let's discuss it later. But I will be happy to cover the time-dependent potential because it is cool and because you are not the only one who is interested. I know from the list. So we will be done quickly before 7, I hope. And we will be done with first chapter of Cartesian propagation of the electron. So next time we meet, I will quickly, for maybe 5-10 minutes, show spin dynamics, which by this time we will start in class, and then we will go to Marcus, which is later, but most of these projects deal with single potential energy surface, where the mass will be much bigger, like 20, mass equal 20,000, which is approximately carbon or something different. And then the range of the reaction coordinate values will be not 10 nanometers as today, but something like 2% of a nanometer, because it is how much like picometers, fraction of an angstrom when the interatomic bond changes just a little. So it will be same code, same principles, but different range of parameters. And there, in this range of parameters, we will design, for those who select this reaction coordinates, we will design the potentials, which will be, again, either through our chemical intuition, or there is a way to extract total energy from computation for couple of lucky guys who selected as it free will. So, time-dependent potential, right? You care where to apply it, or you don't care?
What do you mean?
Time-dependent potential for this model, or for
I don't know, I was originally thinking about the other choice I made, the periodic change of slope for the harmonic oscillator,
okay.
but maybe I don't care.
Mm-hmm. Okay, let's try it probably to. Well, first I will do it to this model because otherwise it will take a little more time to do, and if it will bring to a failure, we will return back to harmonic potential.
I think tau is your time, isn't it?
Tau is a time step. Loops. So we need to loop times tau. But if we do want to do time-dependent Hamiltonian, then so right now I will show the place in the code, but right now before your question, our all operators, Hamiltonian and evolution operator, were time independent, and therefore they were defined outside of the main loop. Due to your question, we need to move definition of the Hamiltonian evolution operator inside the loop and redefine them again and again at each time step. I'm going to comment out everything that was added today and return to the here. V equals barrier 2. So now I'm looking for the first thing where the potential is used. For Braden. I will share the code. You do not need to, well, if you're interested, please follow, but so the energy will also change at expectation value of energy will change at each time step. What else? And we need also for the third this method. And before we set up the here we need to percent it out or remove time dependent part because the variable loop hasn't been yet defined, or we need to set up loop equals 0 before. Okay, let's try. Typically things do not work from the first time. So I'm stopping it just because of the lack of patience. So I'm going to increase the time step and put it in the center. And also for the limiting cases, right now we have a slope of the potential is too small, so you will not see much of effect. So I'm increasing it. And as you observe, the propagation is getting much slower because definition of operators takes much longer than just using them once. So if the things are set up in the right way, the center of the potential will move from left to the right, but it will take some patience to observe it. So it will not be as quick as we used to see. Okay, Braden got some answers to these questions. Any more questions to your projects? Or to the materials that we went over today? I think you got enough input. With another little message. Please let me know if you got MATLAB on your personal laptops or home desktops. Okay? I see it evidently. London?
I do not right now, but I'm like in the process, I guess.
It takes 2 days.
I just gotta fill out the thing.
If you're lucky, it can take a day.
Actually, I could print that out right now and sign it.
You
and
There-
can,
take a
you can
picture.
send that through email, Hayden. You'd use Adobe Reader, use a digital signature.
Just like scroll it with a cursor and do
So
that.
you know how
Yeah.
to do it, right?
Yeah, I have the email with like the form. I just need to actually like sign it and email it back to him.
Okay, because I've one of the group members did a little video recorded presentation how to arrange all permissions and how to download and install it. If anyone needs it, I can share the link, or you can see it on the same channel where class materials are recorded. Is like maybe Tuesday night recording.
Yeah, I use Adobe Acrobat, and then you can create a digital signature, copy and paste that in there, and then send that back to them, and then email.
Not open. Oh, lovely. Okay.
Brain?
Mm-hmm.
You see the potential slowly moves from right to the left. Before the green was under red, now green is above red.
So if I want to speed that up, I would
Change frequency.
frequency inside the code.
Yes.
By what? On what order? Like 10 or like?
Do anything you like,
0.5.
but it should be in resonance with frequency of the oscillator. It should. Right now, it does like 5 full cycles, and try to mode 10. And you can. Right now we determine the slope of the parabola,
Put it on.
but you can convert it into frequency.
That's how I did it, but.
I mean, I could just send them a picture of it. But I sign it. Actually.
Okay, I think
I don't think that.
done. So I'm stopping broadcasting general information, but I will just stay here in case you guys develop questions or want to work on your projects.
No, I don't think you can send a picture of it. I could be incorrect by that. but-
Probably draw.
Because I don't know where you would take a hard copy to.
Yeah. Well, because I just said to like email it back, you know?
Yeah, I literally just, that same email they sent, I just replied it back. Then I got a separate email saying, your MapWorks is being created at this moment. Wait until the next email to activate your MapWork.
Mm.
I mean, you basically, as long as you don't make nuclear missiles, chemical weapons, or travel to Syria, you're
Right.
safe.
You're pretty much golden.
one of the students in my web models works on computational modeling of the self-igniting fuels for space propellants.
Okay.
And he was surprised when signing this. Like, am I allowed?
Yeah, that is actually a good question. Is he technically allowed then?
Well, you can always tell that it is for educational purposes. Right?
True.
We are not in industry.
True. Huh. I laughed at it because I'm like, wait, you could do that? Or like, I didn't know that kind of stuff. It just seemed dumb at first that they would make you sign a form like that for something so simple.
And if you buy the professional license of MATLAB, there are no closures. You just pay something, but then it's for any project.
Okay.
Good night.
You know how to just like draw with your cursor on the software?
On Microsoft Word?
Yeah.
I can do it in Adobe.
Yeah, I wouldn't open on Adobe. Search. There is no shapes. No.
What you could do is assign it in a different software, save it as a picture, and then put it on top of that.
Oh, maybe it's because it's